So 3, 8, 3, 10 is the concept of a function and a relation. We're going to talk about what the difference between them is. We're going to talk about what's called a diagram map. And then we're going to talk about values of functions, domain and ranges, and the graphs of functions. So there's a lot to define, so I didn't sit here and make you copy everything down, so you have this in front of you already. The first term we're looking at is called a relation. And a relation simply maps what are called inputs with outputs. For example, how many, we have a couple track runners here, don't we? I remember there were a few of you that left, 3 of you for the track that day. So in track, right, some days you have better runs than others. Hannah, what's your best run time? What's the race you're running again, Hannah? 5K? No. 5K? What's your best 5K? 21 minutes? What's your worst usually? Or what's the one that you're like not proud of, but it's like...
Maybe like 24.
Maybe like 24. Okay. So the input could be the day. The output would be her running. So the input might be the date itself. I'm not looking at numbers for a second, just ideas. Input the day, and the output you would get is the time you ran the race. You input a new day, you probably get a new output, right? A new time it took you. So the concept of relation is that it just compares two things. Something goes in, and something comes in. Okay? Input, output. That's what we're looking at here. A pairing of these values. Now, the value that we input is called the independent variable because it does not depend on anything. It's independent of choice. So here, you could say, you know what? I'm going to pick Thursday. That's my independent variable for the sake of the example we just used. Or I'm going to pick next week on Wednesday. I can change the input. What depends on the input is the time of her run. That's the dependent variable, y. So x and y are different things that act. Now, to give a better example, I'm going to then really got to go into functions kind of ahead of time before we even get to functions. But think about it this way. What's a good example? Oh, here we go. So, how many of you ride the Metro North? How many of you ride the Long Island Railroad? Or have ridden either the Long Island Railroad or the Metro North ever? Okay, maybe a couple times here and there. Thank you. Please raise a hand there. So if you ride the Long Island Railroad or the Metro North and you go to buy a ticket, what does it ask you at the machine? Where you're going and where you're starting, right? Because you could buy a ticket anywhere, really. Okay, so what would you tell me then? The cost of your ticket is a function of what? Distance. Would that make sense? If you travel longer, you pay more. New York City subway. How does that work?
It's just a flat fare.
It's a flat rate. It's a flat fare. It's the same all the time. That is not a function of distance, okay? You with me so far? So, an easy example to remember is that the independent variable would be the distance you travel. You input that into the machine because it's actually a machine. That's why I'm using this example. You literally type in the machine your distance by putting in where you're beginning, and then it calculates distance, or what's called zones. It uses zones, not really distance, but zone distances. And then what's the output? What does the machine tell you? You put in where you're going, the machine tells you, give me price. Yeah, give me money. It tells you the price, exactly. So the input would be the locations that you're starting at any out of the distance or zones traveled. The output that comes out of the machine would be the would be the cost itself or the price itself. Okay, and this is similar, I had the word cause in my head, sorry. This is similar to cause and effect. The distance traveled causes an effect. The effect is the cost or the price. The independent variable, the thing that you input, that you choose, is your cause. The effect is the outcome. I also like to use the term width of curve and height of curve, and horizontal axis and vertical axis. So let's quickly draw just the first quadrant. If I have a function that looks like this, okay, doesn't matter what the function looks like right now, I can say to myself, okay, at a value of x equaling 10, what's the value of y? And maybe it would be an estimation. In this case, it's a pretty easy estimation. So at a value of x of 10, what would be the value of y? Well, it's around 5, right? If we look at this coordinate, I go over 10, I go up 5, there's my coordinate. So you could say that the width is what? How wide is this? Please, everybody, how wide is this? Oh, careful. How wide?
10.
How high is it though?
5.
So the width of the curve is the independent variable. Look back up at x. This is the width. This is the height. You see what I mean by width and height on a graph now? The horizontal axis, it simply means go along the horizontal. That gives you the independent right there. Go along the vertical. That gives you the dependent value right there. So independent and dependent is x and y, but it's really what you put in and what you get out. So we use x and y all the time, but maybe, just maybe, this instead is the price of a stock as a function of time. What's the independent variable now?
The price.
Think about it. Doesn't the price depend on the day of the week for a stock? If you look up the price of a stock, what do you have to look up really? The time in which the price was made. The price is, so if you know anything about stocks, the price fluctuates as a function of the economy. So the economy changes as a function of time. So tomorrow, the same stock might be a different value. The next day, the same stock has a different value. So as the time changes, the stock goes up, it goes down, there's been a scandal, then it goes back up, somebody new takes over as a CEO, and then they reach their maximum attainable value and they coast for a while. That could be the stock price. But the stock price, P, is a function of time, T. It's always Y is a function of X. Y is a function of X. The dependent variable depends on the independent variable. Okay, the word itself gives you direction in which you should understand, okay, or how you should understand it. It depends upon the other. All right, let's go back to the concept of relations real quick and differentiate between relations and functions. So we take a look at relations. They can be represented 4 ways. The first way is an ordered pair. An ordered pair simply lists the coordinates. The second way is tabular, a table. You see this right here. The third way is graphically. Notice, by the way, these are all the same coordinates, right? These are using the same data. So you have the data represented this way or this way, the exact same data. Well, these exact same 4 coordinates are now on a graph. Or instead of using a graph, you can use what's called a mapping diagram. Your input, I know this is the one that's most unknown to most students. This one right here. It's a way to visually demonstrate domain and range of 2 different things. Okay, it's not necessarily used much in calculus or anything beyond here. Okay, -2 is the input, isn't it? But what's the output for -2? Yeah, it's 2 or -2 is the output. So look, the input is here, but the output is either -2 or 2. That's why this is showing 2 arrows branching off. 0 has an output of 1, 3 has an output of 1. Those both go there. Okay, 0, 1, and 3, 1. Now, the concept of relation simply means it relates 2 variables, x and y. Let's see how a function differs. Anybody know how a function differs from relation? You can ask that question. You could swipe down and see, but there's one specific difference here. There's one difference here. A function, for each input, you have only one output. Only one output. The other way around is not necessarily have to be true. But for every input, you only have one output. So for example, if x is 2, give me a value for y, Max. Any number. 3. Well, if that's the case, and I plug 2 into the function again, I better get 3 out again. I cannot plug 2 in later on and get a number like 4. Well, look, the same input is 2, isn't it? But doesn't the input of 2 have 2 different outputs suddenly? This is not an example of a function. If the same input can somehow give you 2 different outputs, it's not a function. It wouldn't make sense because now it's not a function of the other thing. It doesn't depend on it. Right? This number does not really depend on this number because clearly it's different each way. So again, you cannot have, an easy way to think about it, you cannot have an x variable that repeats itself with a different y variable. Okay, that would not be a function. That would not be a function. So let's look at this first example. You can see this. Graph the relation simply by coordinates. You can use coordinates and tell whether it's a function. So look at the coordinates and make your axes accordingly. Make your axes accordingly, please. So graph the relation and tell whether or not it is a function. So graphically, you're literally just listing coordinates. Your y values, it looks like they range from 1 to 0, and your x values go from 1 to 4. So I'm going to draw my axis like this. Please get used to this, because some of you are still having trouble with this, I've noticed. Look at your data. Look at your function. Those are what govern your graph. Your graph, its size, its increments are based on the data itself. Because the y variable, the data is very small between 0 and 1. I only went from 0 to 1 there. The x went from 1 to 4. So I plot all of these. I've got 1, 1. I've got 2, 1. I've got 2, 1/2. I've got 3, 1/3. And I've got 4, 1/4. Is this a function? It's a simple test. Think about what a function means from the previous slide. Is it a function? Explain why or why not. Is it a function? Why or why not? Bridge, go ahead.
I don't think it's a function because it's in the number 2 column. There's more than one output, so it can't be a function.
Exactly right. Well done. Okay, again, the input of 2 has an output that differs for each of these coordinates. You can't have the same input with 2 different outputs. Where are those coordinates on the graph? Where are they? Do you see them? You see them, right? 2, 1 and 2, 1/2. Everybody sees them? They're right here and here. How are they aligned? You would say they're aligned. What's the word? What are they aligned? Vertically. Vertically aligned. Interesting. Have you heard of something called the vertical line test? Did you hear about this in your earlier classes? Possibly. The vertical line test comes about because when a function, or I shouldn't say that, when a relation has 2 coordinates that are stacked vertically, it means that the same input of 2 had 2 different outputs. The input of 2x had 2 different outputs. You can't have that for a function. So if you could ever take a vertical line, and I'll show you what I mean. If you can take a vertical line and pass it over your data, and if it intersects more than one coordinate, here it intersects one coordinate, here one coordinate, here one. But look here. How many coordinates does it intersect? 2. If it ever intersects the function twice, or 2 different coordinates, you know that it is not a function. I shouldn't say function, geez. If it ever intersects the graph twice, if a vertical line ever intersects a graph twice, it simply means you have multiple outputs for the same input. And that can't be true for a function. So you could say that this fails the vertical line test. Let's see what it looks like on the next slide. The first example on the left is a function. Take your pen, please, if you need to. I used to say this, take your pen and move your pen along. It only intersects with this curve once everywhere we are. But look at this. As soon as you put your pen down, it intersects twice. Over here, it doesn't intersect at all. But you need to test all values. So on the right side, you can clearly see that there are 2 intersections. Those 2 intersections are indicative of the fact that this is only a relation. This is not a function because of these 2 intersections. Questions on the vertical line test. How many of you are seeing this for the first time? Just be honest. It doesn't matter where you are. I just want to know. Vertical line test. Okay. Does it make sense, the concept? If you intersect twice, it means you have 2 outputs for the same input. And we can't have that. So as soon as you intersect twice, you say it's not a function. It's not a function. And the way you can tell is if you wrote down the coordinates. Here's this coordinate. Ready? 2, 2. Here's this coordinate, 2, -2. Well, look, isn't the input 2 the same? Yet there's a different output, 2 and -2. Ooh. Given the following function with the following domain, first, find the range, then graph it, and then finally, is it a function itself? Okay, given the following, I should say equation here, really. Of a given domain. So I don't want you to graph this. It's a parabola. We'll talk about that later in the year, but I don't want you to graph the whole thing. I want you to graph the 4 coordinates. You're given the 4x values for the domain. Find the 4y values, please. Find the 4y values, please. you want to be quick about it, you can plug it in your calculator and go to your table if you like. You can type the equation, y equals 2x squared minus 3x plus 5. You can type that into y1 and use a table. I'll do that on my computer so you can see what I'm talking about in a moment. Again, all you're coming up with is 4 values for y. Switching over to the computer so you can see what I'm doing. If you're done, just look up so you have an idea. I really only want you to do part A. I mean, obviously part B, you're just going to graph those 4 coordinates. And then in part C, you're going to decide if it's a function or not. But here's how you would do it on your calculator. By the way, on your next test, you're going to have part of the test calculator, part no calculator for certainty. Because I'm going to ask you to do things like set up the function and show me the matrix. And then later on, if I ask you with the calculator to solve for the matrix, you can use the calculator for that. But I'm also going to ask you to solve a system using a graphical method and use the solution set range and stuff. So part of this is going to be no calculator. The part that does have the calculator, though, you could use this feature. You type this into y equals by press y equals, and then type in the equation itself. Press second, and hit table. Now, these are all arbitrary values I've typed in the past. I can delete them all because of the fact that I have my table set up this way. Some of you probably have numbers like 1, 2, 3, 4, 5 already there. Here's how I make it so that I can type in a value. Press second, and then table settings. And then choose ask. Oh, look at this. Independ, depend. What do you think those represent? Independent variable x, dependent variable y. So I want to ask the calculator some values for x. So make the independent variable ask. Go over to ask, hit enter. What that will do is that will clear out all the x values in your table.
How do I get out of the exponent?
Press to the right. Got it? So again, press second, hit window, which brings up table settings, and change the independent variable, the x variable, to ask. So now when I press second and go to my table, I can ask the 4 values that I needed. I needed values of -3, -3, enter, 2, enter, 5, enter, 7, enter. Check your answers. You should have gotten 32, 7, 40, and 82. Well, it depends on where you want to go. Where can you go to the table next? Where's the table? Second graph. Again, once you set up your table settings, press second and then hit graph to bring up the actual table itself. So your table settings, to get to those, press second and then window. After you've got it looking like mine, this is all that matters right here. That needs to be on ask. Second, graph. I typed in these 4 numbers. You need to type them in yourself. Making sure to use the negative key down here at the bottom. Please use the negative key. Don't use the minus key. I don't know if it matters actually there. Doesn't matter? Let's see. Yeah, it does. See syntax error? And then go to the error. And it tells me you can't use a minus sign. You're crazy. So you change that to a negative sign, and then it suddenly works. Okay, so 32, 7, 40, 82. 32, 7, 40, 82. So my range, part A, is simply 32, 7, 40, 82. And my domain is -3, 2, 5, 7. Yeah, go for it.
I have a question for 5. If you put it on calculator, you get 40, but if you really solve it,
It's 40.
You just made a mistake. Go check the solution. Check it again. You gotta do 5 squared first.
So it'll be
25 times 2 is 50. 50 minus 15, and then plus another 5. You got it? Yeah. No problem. It should always be the same. So if you have a discrepancy, just check your work for that. So if you graph y, like it says in part B, I need to go up to 80 on the y-axis and all the way to negative 3 along the x. Here I need to get to 80, so I'll go by 20s. Take a look. As long as I label one increment, I know the rest. Is that clear what I'm saying here? I only need to label 1 and 20. The rest will be 2, 3, 4, etc. For those of you that have not been labeling anything, you need to label. You need increments, or else it's not known what you're graphing. So you need at least one number to establish a pattern. Once you put a 1 there, I know the next number is 2. Once you put a 20, I know the next number is 40. Okay, it's always going to be double the previous one, or 1 successively up. 20, 40, 60, up by multiples of whatever that first number is. So simply graphing this, negative 332 is going to be around here. 2, 7 is going to be all the way down here. 5 is going to be all the way up. 3, 4, 5. 540 is going to be over here. And then finally 782 is going to be up here. Look at your 4 coordinates. Any problem at all? Any issue? It's not a line. No, that's fine. I'm saying no. Yeah. It's not a vertical line, but I'm saying, is any vertical line going to cross 2 coordinates? No. So you say it passes the vertical line test. So it is a function. It's also obvious from the data alone to see that this is a function. The data alone tells us it's a function. Because look, do any of your x values repeat? Any repetition in the x values? Any? None. So that means that there's not going to be a double input with a different output. We don't have to worry. It will definitely be a function. Part C is yes, it will be a function. Okay? Now, keep in mind, please, that the x values are the domain and the y values are the range. Domain, range, domain, range. Because the next example, we're going to use that terminology now. So we look at this example. Determine or give the domain of each function. Give the domain of each function. So we've got 4 functions. Here's where you have to actually think outside the box. We're going to have to think about some restrictions. It's not obvious what those restrictions actually are. Okay, it's not obvious. But it's a little bit difficult to see here by looking at this just directly. Give the domain of each function. How about the first one, part A? What would restrict our domain for part A? Would any values make this not possible? No. Good answer. How come?
Because the only possible thing is around here is x squared plus 4 equals to 0.
Correct. Why?
Because
You can't what?
you can't divide it by 0.
You cannot divide by 0. You guys remember that, right? Division by 0 is undefined. So the denominator can't be 0. But could you somehow make that denominator 0 for part A? Is there any number you can think of that would make that 0? Pick any number for x. Whenever you square a number, it always becomes what? So you're going to have a positive plus 4. Is that ever going to be 0? A positive number plus 4, is it ever going to be 0? Of course not. Only negative 4 plus 4 would give you 0. So Ashley is absolutely right. The first problem, the domain is all real numbers. The domain for the first problem is all real numbers. You can write out those 3 words, or you can write the following. This means the following. X is contained in the set of real numbers. Real number set is drawn with like 2 vertical R's slashes. See those 2 lines? That's not a typo. It's not a mistake by me. X is in the set of real numbers. It's just the way to see it. You might see it in like a textbook, but if you wrote all real numbers in the test, that's fine with me. Part B. Mr. Brown, help me out. What values of x would make this denominator 0? You're good with intuition, that's why I asked you. You're able to see stuff. Negative 2? Yeah. Absolutely.
And 0.
And 0 or 0, either one. Negative 2 and 0 are not going to work. Plug in negative 2. You get a 0 times negative 2, which is 0. Plug in 0. You get 0 times 2, which is 0. So if you set the denominator for number 2, or part B, you say that the denominator cannot equal 0. We can see that, well, x can equal 0, and x can equal negative 2. Those are the two things that would make the denominator 0. So if you're writing out your domain, you could say all real numbers except for 0 and negative 2, if you want to. You could write your domain in interval notation. You could do this.
Can we write like x does not equal like the equal sign attached to it?
So either one of these interpretations, yes, is good, okay? So look at the first way to write it. The first way to write it is, it's lengthy, but it makes sense. From negative infinity to negative 2, you're all good. At 2 and negative 2, we got a problem. From negative 2 to 0, we're all good. At 0, we got a problem. And then from 0 to infinity, we're good. Okay, that's interval notation up top. And this is just really, I mean, it is set notation technically, but set notation would be with inequalities. And again, you could also write the words, all real numbers except 0 and 2, and negative 2. How about part C? Part C is a bit tricky.
Is it anything but negative numbers?
Good. You can't have negative under the radical. So therefore, the radicand, here's part C, has to be 0 or what kind of numbers?
Positive.
So we say greater than or equal to 0. Again, think about it logically for part C. Underneath a radical, you cannot have negative numbers. So whatever is under the radical has to be 0 or positive. What numbers are 0 or positive are numbers that are greater than or equal to 0. So whatever is underneath the radical in part C, you simply set that greater than or equal to 0 and solve. Add the x over, you get the following statement. And what does this tell me? Really, this means x is less than or equal to 2. Try numbers. Try numbers, please. By all means, try numbers. Pick a number that's not less than or equal to 2. What's a number that's not less than or equal to 2? Give me any example number not less than or equal to 2. 5. Okay, plug 5 in part C. You get 2 minus 5. What is that? 2 minus 5. Negative 3. If we take a square root of negative 3, it's not a real number. We'll talk about what that number is a little bit later down the road, but it's not a real number. So a number like 5 will not work. Yes, Annette?
What's a radicand?
A radicand is the expression underneath the square root. And the square root is called a radical. The square root symbol, this thing, is called a radical, and the number or expression underneath is called a radicand.
So 2 minus x
Is the radicand.
Radicand sounds like a Pokemon.
Is it?
Isn't there a Pokemon called Raticate?
I don't know, it's possible. I don't know Pokemon well. I know Dragon Ball Z really well. I'm not a Pokemon person.
Yeah, Raticate.
It's like F, G,
Oh, so I didn't even go over that. Thank you. That's a great question. So George poses the question, what's going on with these variables next to x? So functions are written as f of x or h of x or g of x instead of y. Remember earlier in the year, this was y equals? Each one of these, we had this. Y equals. Y equals. Instead of writing y, we can name functions with another letter. And sometimes you could use the letter of what it means. So if I'm looking at cost as a function of production number, it would be C of n, and n goes here. Cost as a function of n being the number of production particles produced, or objects produced. So this is simply h of x, g of x, k of x, f of x. Those are other ways of writing the variable y. That's all it is. But you're writing it as a function because this is indeed a function. It could be anything. No. It could just be anything, any letter. It usually comes from whatever the problem is dealing with. If the problem is something like population as a function of time, it might be P of t. Population as a function of time. So P parentheses t, and then t down here. So P of t is your y really, and t is your x. Okay? Good question. I should have mentioned that. Thank you, George. How about the fourth one, part D? Part D is very similar to part C, but there's some difference in it. You have a radical still, but where is that radical? Physically, where is it? In the denominator. What can I not have in a denominator? So now, instead of writing greater than or equal to 0, just greater than 0. Again, think about it for a second. Pause. Underneath the radical has to be 0 or positive. But since the radical is in the denominator, it can't be 0. So what's underneath that radical there has to simply be positive. So it was 2 over 2x minus 8.
Wait, so
Go ahead.
if x equal 2 and you get 4 minus 8, you square root of negative 4.
You would get, if x equals 2, you get 4 minus 8. That's negative. It's not going to work.
Yeah, so isn't it the answer to it x greater than 4?
Let's figure it out. Let's go through it. We set the radicand greater than 0 because, again, it's got to be positive or 0 because it's under a radical, but because it's in a denominator, it can't be 0. So this is really saying this has to be positive. This has to be positive. And then when you add 8 over and divide by 2, you're going to get x is greater than 4. X is greater than 4. So yeah, 4 doesn't work.
With the answer.
Yeah, okay. 4 doesn't work, right? If you plug 4 in, you're going to get 0. But anything greater than 4 will work. Try 5. 5 works, you get 2 under the radical. Try 6, you get 4, etc., etc. Okay, so take whatever you have here and set it greater than 0. So this is your domain for this function. Why is it important to represent a domain? Please, do me a quick favor. Do me a favor. I need to prove this to you. Don't think I'm crazy. Go to your calculator and type this into your calculator here. 2 over the square root of 2x minus 8. You might run out of time at this point, just to give you a heads up. 2 over the square root of 2x minus 8.
How do we do the over? Can we just do division and that way?
I'm not going to have you finish this tonight with a video. I'm going to continue tomorrow with this actually. What did you say?
Nothing.
Over is division. Is that what you asked?
No, yes.
Here, I'll show you online, please. 2 over, parentheses, second square root, 2x minus 8, close, zoom 6. Look where the graph starts on the x-axis. It's going to start right here at 4.
What?
Isn't that 4 right there? And then isn't it everything greater than 4? Notice,
That's
the
meta.
graph does not exist for values of x that are less than or equal to 4. Our answer we got was x is greater than 4. Look at the graph. It starts at 4 and it's everything to the right. Okay, the domain is really saying where is the graph going to be acceptable. So tomorrow I have you guys, right? Yeah, day 6 I don't.
Yeah.
So tomorrow I need to finish this section and I'm going to jump right into section 3.9. Is that clear? Okay, so you don't have homework tonight that's due tomorrow because I really didn't finish it and I have a good amount to do still. I don't want you to watch all of this. This is stuff that I want to talk about a lot. So tonight what you can do, maybe do all your problem sets that you can do so far. Because keeping in mind that your problem set is due when?
Friday.
On Friday. Okay, tomorrow we're going to finish up this section and we'll do 3.9. That problem set we'll do on Friday. So do all your problem set at least tonight except for 3.8, 3.10, and 3.9.
Just the problems that's due.
Friday. It's always the class day before the test. And since the test is Monday through Friday. Yep. What's up, Nick?
Does this look okay? Because you can't really see a lot, but I don't know how else to represent it.
Yeah, you're good. I mean, so it's that region, obviously, right?
Yeah.
Yeah. So where you have the overlap of several colors is the solution region. That's fine. Yep.
Can you tell the numbers? They're kind of covered.
Okay, fine. That's good. Yep. Thanks, Kate.
Rainbow's not here today. Right. Is she not here?